Yeah, at least my class before, they had like, they were saying that they had like 4 midterms this week. That's a benefit for me. I'm only taking 2 classes right now, and one of them is research, so I only have 1 midterm. Which calc? Calc 2? I don't know, you guys are taking a lot of different calcs in here. Calc 2, okay. Solid mechanics. That's not a bad class. Alright, well, lucky for you, this week we don't have a quiz this week. We're gonna have it sometime next week, but we'll talk about that more on Wednesday. It'd be more like Wall Street bets. Yeah. Hey, they had a good day today. I just checked it. Okay, so before we get started, I want to talk about the first, or the second quiz rather. So I'm not done grading the second quiz quite yet. I'm like a little more than halfway through, so I'll finish them by this Wednesday for sure. But again, I graded about half of them, so if you have what appears to be like a really bad score right now, don't freak out. It's Canvas trying to automatically grade your quiz, and it's really bad at that. So again, I'm going to get them graded by this Wednesday. And I had a few questions if I was going to curve the quiz or not. So I'm not going to curve individual quizzes, but at the end of the semester, I'll see, what the average grade is, and then I'll apply a curve then, if needed. And we're going to go over the quiz today. So, I posted the solutions after the quiz, or maybe on the weekend, something like that. But we're going to go over the quiz today because I think it's going to be really useful to go over those solutions again, because I know this quiz was harder than the first one. I didn't plan on it to be harder, but yeah, it was a lot harder than the first one. So, some quizzes will be really easy and some will be hard. I try to make them all like relatively the same for how challenging they are, but that could be hard to kind of guess sometimes. Yeah, last one took a good amount of time. Yeah, so yeah, like a lot of these with array addressing, you really need to know like what you have to do right away, and if you don't, it can take a while. Oh yeah, so also, I know since we're talking about time here, I know a lot of you guys said that you would prefer if we had more time on the quizzes, so 15 minutes is already a good chunk of the class time, so I'm not gonna give more time, but I'll give less questions. And so we'll kind of do it that way, but I'm trying to think about what's the best method for you guys for your quizzes from here on out, because I want it to be fair, I want you to have a lot of time, and I want you to challenge you too, but I want it to be like not super stressful. Okay, we aren't being asked to create things yet, we're just doing commands. I don't think they're hard, we just need more time. Yeah, so I'll give you just less questions, because 15 minutes is already a lot. Okay, yeah, if you can't hear me, you don't know what I'm saying right now, but it's quieter than usual. I might have messed with my audio interface, I don't know. I'm gonna leave my mic levels where they're at, because if I turn it up a little too much, it starts to clip, so just, I guess turn your speakers up. Okay, making sure I was recording. Okay, so today we're going to first go over the quiz 2, and then after that we're gonna do a little review on the element by element operations from last time, and then we're gonna do matrix operations, and if we have time we're gonna start plotting, but I don't think we're gonna get there today. Let's get you out of here. Okay, so quiz solutions, again, they're posted online if you want to get the script there, but we're going to go over it in here. Let me pull up the chat too. I know you see that like weird box in the bottom right, that's the chat. I'm just going to pull it up for now. Okay, so problem 1, you can see it up here, we had to create the following matrices. So I let you do any method that you wanted to use. So you could do row by row or column by column, like whatever method you prefer. And then after that, from these two matrices, that's the key word, we have to use array addressing and other techniques like the transpose operator to create this matrix D. Then after that, we're going to use the concatenate function to create a multi-dimensional array called C, where this matrix up here, A is the first layer and then B is the second layer. Alright, so let's do the first one first. So we're going to make our matrix A. I'm going to do it row by row. Some of you did ln of 5, and that's what you would do in like a math class, but MATLAB is, I guess you could argue, a little bit weird. For the natural log in MATLAB, it's actually log. And then log base 10 is log 10, and then whatever. So again, natural log is log, and then 5. We have 2 and 4. 9, -2, 10. 12, 12, -8, and 4. Okay, so there we go. There's matrix A. And now we need to make matrix B. Let me address this. Okay, so B, we're going to do 2, 10, 12, 3, -4, 34, 21, and 0. Also, I want to point out that making these matrices, that was only 2 points out of 10 for this problem, just because it's so basic now. So, you know, the main thing for this quiz was array addressing for the most part. So that's why that was 6 points. So if you didn't get any points for part B here, then that was a lot of points to miss out on. Okay, so part B. From our matrices A and B, we're going to use array addressing and other techniques to create the following matrix D. So I'll do D equals, and if we look at these first 2 rows here, you see that it's the first 2 rows and first 2 columns for matrix A. So we want to start building a matrix where our first 2 rows and our first 2 columns are this part right here in matrix A. So I'm making a matrix. I'm going to start it with brackets here. So I'm going to put in a left bracket. And we're using array addressing, so I have to reference matrix A. So I'm going to put in A. And now I want rows 1 to 2. So 1, 2. So far we're getting the first row here and the second row here. But I want to constrain that to the first 2 columns in matrix A. So I'm going to do 1 to 2. I'm just going to do this right now and we'll see what it looks like. Okay, so right now this is what we have. And it's just this, well, first 2 rows and first 2 columns in matrix A. Alright, so we got that part. We have this first part here, but now we need the other part. So what, I guess you want to think about what you are trying to achieve here. So I have the top part of this matrix, but I want to have the bottom part. So to do that, I'm going to put in a semicolon. Okay, because remember, a semicolon with when we're making a matrix, that makes a whole new row. Okay, so we're going to have a semicolon here. And then I'm going to do B, because I want to reference matrix B now. And you see that we have -4, 1, 34, and 0. So that's this part in matrix B right here. But it's transposed, so these rows, they were transposed or flipped with the columns. So you can see that if we're looking at this, we kind of flipped 34 and 1 on there, like along this axis here. Okay, so we have B. I want to get rows 2 to 3 in B, because we're in rows 2 and 3. And then we're going to get columns 2 and 3 in B as well. So columns 2 and 3. But again, we have to transpose this so we can get this form down here. So I'm going to put in an apostrophe. That's going to transpose. Then we'll put in the last bracket. And then we'll run that. And then we have the matrix that we wanted to create for matrix D. Okay, any questions on this part? I think this was probably one of the more tricky questions. This one and the last one. Okay. Okay, so part C, we have to use the cat command to make a multi-dimensional array called C, where A is the first layer and B is the second layer. So I'm going to do C equals cat. And remember, when we make a multi-dimensional array with the cat command, we have to put in a dimension of 3. So a dimension of 1, that appends an array below our current array, and a dimension of 2 appends an array to the right of our current array. Using a dimension of 3 is when we make a multi-dimensional array. Okay, so that's why we have 3, and then we want to put in the first layer, so that's matrix A, and then the second layer is matrix B. Right, let's run that, and then there we go. We have our multi-dimensional array. Okay, any questions so far? Alright, problem 2. So we have some arbitrary multidimensional array E. So when I say that, I just mean some multidimensional array. It doesn't matter what's actually in that array. It just means I have some array called E. When you use the cat command, do they have to be the same size? Yeah, they have to be the same size. Okay, so we have this arbitrary multidimensional array E. That's a lot to say. And we're going to use array addressing once again to specify the following. Alright, so the first one, do part A. So we want to look at the first row of the first layer, all of the first row in the first layer. So I want to reference that 3D array, so I'm going to put in E. And I want to look at the first row, so I'm going to put in a 1. And I want all of that first row, so that means every column in that row, so I'll put a semicolon. And then I want to look at the first layer for that multi-dimensional array, so I'm going to put in a 1. Okay, there we go. So that's the first part. And then part B, I guess it's not really part B, but whatever. We have B equals, so we want to get the value in the third row, the second column, and the second layer. So I have E, I'm going to go in the third row, second column, and then last argument is going to be the second layer. Alright, so there we go. Alright, any questions on problem 2? I'm going to comment these out just because I actually didn't make, a matrix E or a multi-dimensional array E. So if I run this, I'm going to get an error. And again, that's just because I didn't actually create E. So I'm going to comment these out. Alright, problem 3. So this was the most difficult one, I know that. So I'm actually first going to make the matrix F. You didn't have to in the quiz, but I'm going to make it right now. So we have F equals 5, negative 2, 5, negative 2, 10, 12, 10, 1, 3, negative 11, 22, 66, 34, 29, 69, 24, 101, 33. Alright, there's our matrix F. come up here. Okay. Alright, and now what we want to do from this matrix is make a whole new matrix called G. And again, we're going to be using array addressing in other techniques. I think we have to transpose again. Yeah. And we're going to make this matrix G here, which contains, or basically the first row for matrix G is the first column for matrix F. And then on the second row, the first two rows, on the second row in G, that's going to be consisting of the first two rows in column 2 of F. So that's these values right here. And then to the right of that, so the last two indices here, those are going to be the first row and the third row in column 4 in F. So I know that's kind of a lot to take in. So that's, you kind of need to break it down, I guess, step by step. So I'm going to do this all in one line. I didn't tell you it had to be on one line, so you're not going to be marked down for that, but I'm going to make this on one line. Alright, so we have G equals, and I want to make a matrix here, so I'm going to have my brackets once again. So I'll put in a bracket. And let's do the first row first. So I need to look at matrix F, and I want to get all of the rows in column 1. So I want to get all of these rows in column 1. So I'll do colon, comma 1. And right now if I do this, it's just going to be a column vector. So that's what we have. But I want to make this a row vector so we can get the first row for G. So to do that, I have to transpose. Okay. I'm actually going to break this down a little bit more. No, I won't. Okay, I'll leave it like this. Okay, so there we go. That's the first row. Now let's start working on the second row. So I'm going on the second row now, so I'm going to put in a semicolon. And I'm also going to have 2 more brackets. Let me space this out a bit, and it should still work. Let me do it like this first. Okay. Okay, so within these 2 brackets here, I'm going to make the second row for matrix G. Alright, so the first thing we need is the first 2 rows in column 2 of F. So let's put in F, and I want the first 2 rows, so I'm going to do F1 to 2. So that'll be rows 1 to 2, and I want to get column 2 as well. So that's rows 1 to 2 and column 2 in F. Alright, now I'm going to put a comma. I can also just put a space, but I'm going to put a comma right now. And for the last part here, for numbers 12 and 29, we want to get the first row and the third row of column 4 in F. So first row, third row, column 4. So I'm going to do F. And here, let's do this. And I want rows 1 and 3. So I'm going to put those in brackets. So remember we talked about this maybe last class, something like that, where if I want to specify some rows that aren't in kind of consecutive order, I put them in brackets like this. So this will be F, rows 1 and 3. And now I need to specify the column. That's going to be column 4. I still have some things that I need to do though. Currently, -2 and 1 and 12 and 29, those were basically what we have are column vectors. But I need to transpose them to be row vectors. So let's also throw in an apostrophe here and an apostrophe over here. Okay, and then I run that, and then we get our matrix G that we wanted to get down here. So I'll go over this one more time, because again, I know it's a lot, but before I do that, are there any questions? Okay, I'm going to go over it one more time, and maybe you'll have questions then. So let me just comment it out. Don't say that. It's a lot to take in. You guys are going to be fine. The extra brackets, I think you mean like this bracket here and here. Oops, sorry. I don't think you have to put them in. That was for readability. Yeah, you don't have to put them in. I put them in when I first did it myself just for readability. So I know that this is, within these brackets here, that's the second row. But yeah, you don't need them. Okay, so let's do this one more time. Okay, so we have our matrix F here, and I want to make matrix G, and I'm going to do this on one whole line. Okay, so we have G. I'll just delete this, why not? Okay, so we have G equals. Oh, that's weird. On my one computer, it can't read your emoji. So it shows like, well, it's like empty brackets, whatever. If you didn't get the brackets all around it, then you're probably going to be docked 1 point. If I already graded your quiz and I docked you off like 5 points or something, then let me know. Alright, so we have G. I'm going to put these brackets here now just so we kind of get a better idea of what we're doing. First thing, I want to get the first column in matrix F, and I want to make it the first row for matrix G. So to do that, we have to do array addressing. So I'm going to do F. I want to get all of the rows in column 1. So right now, it's going to be a column vector, because all I'm doing right now is getting all of the rows in column 1. I want to take all of those values and make it a row vector for matrix G. So I'm going to transpose it. There we go. Now we have a row vector. And now we want to make the second row for matrix G. So I'm going to put in a semicolon. And again, I'm going to put in brackets here just so it's, for me, I can read it better this way. So within these brackets, I'm going to have row 2. So first thing, we're going to get the first 2 rows in the second column of F. So I'm going to do F 1 to 2. So that's the first 2 rows, and I want to get column 2. So I put in a 2. Currently, this is a column vector. So if I go in the command window and I do F1 to 2, comma 2, you see that's a column vector. I need to transpose it to be a row vector down here. So I'm going to transpose it by putting in the apostrophe. And now we need to get the last 2 values, 12 and 29. So we're going to do F. We want rows 1 and 3. So I know right here, there's a lot going on here. So we have F, rows 1, comma 3. Okay, rows 1, comma 3. And now I need to put in a comma, and then I need to specify the column that I'm looking at in F, which is column 4. And again, right now, if I do F in the command window, F 1, comma 3, comma 4, it's a column vector right now, so I need to transpose it to make it a row vector. So I'm going to throw in an apostrophe right there, and then we run it, and then we get our matrix G. Okay, so a lot, I know, but are there any questions on this now? Hopefully it kind of cleared everything up here. Okay, I'm going to assume that you guys get it then, but if you have any questions, let me know. Is there a question? No? Okay. Alright, so let's start on today's lecture now. So, first thing we're going to do is review element by element operations a bit. I have to make it centered. Gotta do it. It's still not. Oh well, I'm not gonna deal with it. Okay, here we go. Alright, so first thing, reviewing element by element operations. So I'm gonna go back a bit. And we're going to go over multiplication and division. So remember last class we went over element by element operations for multiplication between arrays. Alright, so here we go. We have a row vector A and a column vector B. And with those, I could do an element by element multiplication. That's actually, sorry, I'm going to go back one more to here. So here we have two row vectors, A and B. And we're going to do element by element multiplication with them. And when I do that, we get another row vector for the output. So we have 1 times 0 is 0, 2 times 2 is 4, 5 times 3 is 15. And then we saw if I have a row vector and a column vector, our output in this case is going to be a 3 by 3 matrix. And it does this by, it's still going element by element here. So we're going 0 times 1, and then we have 2 times 1, and then 4 times 1. So all of these elements in row vector A are being multiplied by every single row, basically, in column vector B. And then we go on to the second line, so we have 0 times 2, 2 times 2, 4 times 2. And then the third row, we have 0 times 3, 2 times 3, 4 times 3. So something of note, these sizes are different. So I had, let's do review. I have 0, 2, 4. And B, that's going to be 1, 2, 3. And if I go in the command window here, and I type in size of A, size of B, we see that those sizes are different. But if we do element by element multiplication, it doesn't matter if the sizes are different, they just have to be compatible. And in this case, they are compatible, and that's what leads us to get a 3 by 3 matrix. And we could even add a whole nother row to matrix or to the column vector B, and we could still do this operation here. So let's do size of A and size of B again. We see that the sizes are different. But if I go in here and I do A times B, and remember element by element operations have the period before the operator. If I do that, then this time I get a 3 by 4 matrix. Or sorry, 4 by 3. What would make them not compatible? I don't think anything would be not compatible for this operation. I just emphasize the term compatible because once we get to matrix operations, they have to be identical. So I just kind of want to differentiate that. Okay, so here, again, our sizes were, we had a 1 by 3, and then we had a 4 by 1. So, this time they're totally different, right? Even the magnitude is different. But we can still do that operation here. Okay, and then we went on to element by element multiplication between matrices. And in this case, the sizes actually have to be identical. And you'll see for matrix multiplication, the sizes don't have to be identical. I think I might have just said that a minute ago. That's wrong. For matrix operations, they need to follow rules that we have in linear algebra that we're going to go over today. But for element by multiplication between matrices, the sizes have to be identical. So here we have two matrices that are 2 by 3, and if we multiply them, we're going to get a whole new matrix that is the same size. And we're going element by element as the name implies. So we have 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, and so on. Okay, and you see here, if the sizes are different, then we're going to get an error. Okay, then we talked about vectorized functions, so that's stuff like square root of x. If x is a vector, then our output for that is also going to be a vector. And same thing for trig functions too. Let's do vectorized functions. So if I have a vector x, let's do from 0 to 0 with a step size of 0.01, and we'll go to 10. If I do r equals sine of x, type in the length of r, and our length here is 1001. If I want to make a variable called s, where that's going to be, let's say, r times cosine of x, let's run this now, and you see that we get an error here, because it's trying to matrix multiplication, which we'll talk about in just a few minutes. So what we have is r is a vector, and in cosine of x, that's also going to be a vector. And in this case, we would want to do element by element multiplication, so we have to put in that period. And then we can do it. And then you see here that our length is 1001. Okay, so basically you need to make sure that when you have a vectorized function, like a trig function, or a square root of some vector, that you're doing element by element multiplication, unless you specifically want to do matrix multiplication. Okay, so I think we left off on here last time, if I remember right. But we can do element by element division, and that's just using our regular division operator, which is a forward slash. Alright, so if we have two matrices A and B, well, we have A is 10, 20, 15, and 5. And B is, we have 2, 4, 5, and 3. I'm going to show them here. If I want to do element by element division, we can do that, again, with our everyday division that we have. So I'll do C equals A, and then we're going to put in the period, because we want to do it element by element. And then we're going to use a forward slash for the everyday division that we have. Okay, so this will do 10 divided by 2, 20 divided by 4, and then 15 divided by 5, and then 5 divided by 3. Alright, so that makes sense. And then on a related note, I think we talked about, left division here, which is to solve a linear system of equations. We'll talk about this a few times throughout the class, because it is pretty important. It's actually very important for if you're writing like a big script, and like basically you would convert a differential equation into a linear system of equations, and you would solve for it using a method like this. But anyways, that'll be for later on. I just want to briefly touch on it now. So even from our same matrices A and B, if we do left division, we're basically solving for this linear system of equations, which, again, we'll talk about in more depth for the theory a bit later on. But if I do A, and then a dot, and then a backslash B, this is going to be different. Okay, so if I run this, then we get that. Actually, I shouldn't even, I guess I do need the dot. Okay, so this dot is actually even a little different than a backslash B, but again, we'll talk about this later on once we get to solving linear systems of equations, which will be towards the end of the semester. Okay, here we go. So, summary, for element by element operations on vectors, the dimensions, they have to be compatible. The sizes don't have to be identical. But once we do element by element operations on matrices, they do have to be absolutely identical in size. Alright, let's do, I'll do this again. Okay, so I know a lot of you haven't taken 250B yet, so this stuff is actually kind of, it's like a combination of teaching you MATLAB and math right now. So you're gonna have to bear with me, but okay, I'm gonna try to teach you as best I can here. And that'll be for multiplication once we get to that. Okay, so MATLAB has array operations, which is what we just covered. That's element by element operations, but it also has matrix operations. So a matrix operation, it'll make more sense. So it'll make more sense once we start doing matrix multiplication. And we're going to get to that in just a few minutes. But first off, let's do it for addition and subtraction. So, matrix operations, they're going to be the same as an array operation. Remember, an array operation is the same as element by element operations. So for addition and subtraction, both of those operations give us the same output. So I can do A equals 5 plus 2, and this will be like matrix addition if you want to think of it that way. It's really, it seems kind of weird to say that. But, you know, we have A equals 5 plus 2. Our answer is going to be 7. If I do an element by element operation on this, I'll also get the same result. So I did this before and I got an error, and I know why. So if you put in a space both before and after, so if I do 5 space dot plus 2, I'm going to get an error here. It says invalid use of operator, and that's because I have a space right here. So if I delete that space, then MATLAB will go, okay, yeah, it's fine. Right, and you see that B is 7 once again. So here there's no difference if I put a period or if I don't put a period. It's going to be the same thing for addition and subtraction. So the difference comes in here for multiplication and division for matrix operations. Okay. So we're going to go here. So first thing, I don't like when I have little screenshots like this. It's harder to look at. Okay, let's do this. We have A equals 808. And then we have B equals 2, 3, 2, 3. So we have a row vector A and we have a column vector B. Let's make those lowercase. Okay, so if I do an element by element operation here, so I'll do C equals A and then dot, so it's element by element.
The columns and rows have to be equal.
Yeah, so that's going to be the point that we get to in just a second here. So if I do C equals A and then dot star B and I run this, then we get this 3x4 matrix here. Then if I do D equals A times B, this will be a matrix operation or matrix multiplication. I'm going to get an error here. So my explanation here, don't look at that. That's not correct. So that was a typo from last semester. They don't need to be identical. I'm going to skip this now. The amount of rows needs to be equal to the amount of columns in the other array. This will be explained in a lot more detail, so just hold on. But this example is just to show you that element by element multiplication is going to be different than matrix multiplication. All right, I'm going to take that out. So let's start out with multiplication or matrix multiplication between two vectors.
Wait, can you do element by element addition, even if it's not equal in length or columns?
Well, yeah, that would be with a vector, so no, they would have to be the same size. If they're not equal in length, you could put a placeholder of like a 0.
For element by element, right?
Yeah, they would have to be the same size still. Okay, so vector multiplication, if I have a vector A, so we're going to do 1, 2, 3, and a vector B, we have 4, 5, 6. I should have semicolons here. So I'm going to do A, comma B. Okay, so we have these two vectors, and if I want to do matrix multiplication here with these two vectors, we can do that. So this is when we're going to start to kind of talk about the linear algebra kind of part. So I'll do C equals A times B. So this is matrix multiplication here because I don't have a period. So if I run this, then I get a scalar for the output.
We're kind of doing this in physics, actually. Like,
Oh, you are?
Yeah.
Oh, that's good. Okay, so maybe you have like a bit of review
Yeah,
then.
a little bit.
I'm going to put a comment here and say that this is matrix multiplication. And then we'll do element.
So is element by element like a cross product or what?
It's kind of like a dot product, but for each kind of row.
Oh.
Okay, so if I do element by element multiplication here, and then I'll do capital V equals A, and then dot star B. And if I do this, that's when we get a 3 by 3 matrix here. So really it's kind of distributing 1, 2, and 3 with 4. So we do 1 times 4, 2 times 4, and 3 times 4. So kind of distributing instead. Okay, so that's the difference there. So matrix multiplication, we get a scalar in this case. And element by element multiplication, we get a matrix. And the order matters here. So what you're going to see in a few slides, actually right now, 2 slides, is we're going to do, instead of A times B, we're going to do B times A. And then we'll see how it kind of changes things. I'm going to put this up here. Okay, so let's break this down. So this is basically math time now. So I shouldn't be your math instructor, but kind of am, because again, I'm going to complain that linear algebra isn't a prereq for this. So what we're doing, we have a row vector A and a column vector B. And to do this matrix multiplication, we have to multiply each column in A with the corresponding row in B. And again, you'll see that order does matter in the end. And we're also going to talk about the sizes of these row vectors and column vectors in a few slides as well. But I first want to show you the kind of, just the bare bones, the math behind it first. So to get this output, we have a scalar. We're doing 1 times 4. And then we have plus 2 times 5 plus 3 times 6. And then if we simplify that, we have 4 plus 10 plus 16. And then we get an answer of 32. Alright, so in this example, the length has to be the same. So remember from a few examples ago, when we did element by element multiplication for this, I could add a whole new row and this column vector B here, and I could still do it. But for matrix multiplication, for this example, I can't add a new row. I'll show you that here. So let's add a new one. I'll put in 5. And if I run this now, oh, sorry, that's element by element multiplication. Let's comment this out. So if I run this now for matrix multiplication, then we get an error. Okay, so here we have a length of 3, and column vector B also has a length of 3. Okay, if I switch the order, now we're going to get an output of a 3 by 3. So for matrix multiplication, the order matters for how you have it. So if I do A times B, we get a scalar. Okay, we get a scalar. And if I do B times A, we're going to get a matrix. So I'll do E equals B times A. And you see now we get this matrix here. Matrix. Okay, so what we're doing here again, kind of behind the scenes, we have 4, and this is going to be, well, think about it this way. Each row in B is going to be multiplied by each column in row vector A. So we have 4 times 1, that'll be the first index in our matrix. And we have 4 times 2, that's the second index in our matrix. And then we have 4 times 3 is 12, that's the third index in the matrix. And we're going to keep doing this now row by row. So now we have 5 times 1, 5 times 2, 5 times 3, 6 times 1, 6 times 2, 6 times 3. Right, and then we get this matrix here. So you might be wondering, like, how can I know what the size is going to be before I do it? We're going to talk about that in a second. And we'll also talk about how we can know if matrix multiplication is actually going to work or not. So first thing, we're going to talk about how we can know if the matrix multiplication is going to work. So you want to first think about how we have 2 matrices. And remember, when we talk about matrices, we say that it has a size of m by n. So m, that's the number of rows, and n is the number of columns. So matrix multiplication looks like this for 2 arbitrary matrices here. We have m by n, that's the size, multiplied by some other matrix that has a size of m by n. So right now it's completely arbitrary for what those sizes actually are. And to be able to do this matrix multiplication, the columns in our first matrix, they need to match the number of rows in the second matrix. So if we look at our example that we just did, for A times B, I have 3 columns in matrix A, and I have 3 rows in matrix B. So because those are the same, that means that I can do that multiplication. And a great way to kind of confirm this is if you actually write out the sizes yourself. So the multiplication that we're doing here is 1 by 3, that's the size, multiplied by a size of 3 by 1. Alright, so you see that these inner numbers are both 3. So since they're the same, that means that we can do this matrix multiplication. And remember, we try to flip the order. So instead of A times B, we tried to do B times A. So this has a size of 3 by 1, and this vector over here has the size of 1 by 3. So these numbers match, and we could do it. Did I just say that we couldn't do it? Sorry, I misspoke then. But because these numbers match, we can do the operation, as you saw right here, for matrix E, and that gave us a matrix, right? So let's I guess recap again. A times B.
A scalar.
What was that?
Why is A times B a scalar but B times A matrix?
Yeah, we're going to talk about that too in the next few slides.
Okay.
That's a good question though. Okay, so we had A times B. So A was the size of 1 by 3, and B was the size of 3 by 1. So the number of columns in A matches the number of rows in B. And again, we can look at these inner numbers. That's what they are in the end. The columns in A and the rows in B. And they match, so we can do this matrix multiplication. Let's unsuppress the output. Okay, so that was a scalar. And again, we're going to talk about why that was a scalar in a second. And then we did matrix multiplication of B times A. So we had a size of 3 by 1. We have 3 rows and 1 column, and then we multiplied that by a size of 1 by 3. Our inner numbers match, so that means that we can do that multiplication. So if we do that, then we get a matrix in this case. So that's why the order matters. So up to this point, before I talk about why we have different sizes for the output, are there any questions? Okay. So now to actually know the size that we're going to get. So I'm not going to get too into depth for the theory here, but I'll explain how you can know what the size is going to be ahead of time. So this is going to be under the assumption that we already know that we can do the matrix multiplication. So if the number of columns in the first matrix matches the number of rows in the second matrix, then you can do the multiplication. So we're at that point now. And now we're going to think about the size that we have. So
wait,
to know,
if inner numbers are not 1, then it won't be a scalar then, right?
it depends. It depends. I'll show you how you can know the size right now. Okay, so if we know that we can do the multiplication, then if you want to know what the size is going to be, we're not going to look at the inner numbers anymore. We're going to look at the outer numbers that we have. So that'll be this outer number and then this outer number. So if we go back to our example that we did before for a times b here, if we look at the inner numbers, that's going to tell us we can do the multiplication. So here, the inner numbers were both 3. That means I have 3 columns in A, and I have 3 rows in B, so I can do the multiplication then. And then the outer numbers are both 1, so that means 1 by 1, that's a scalar. So we get a scalar for the answer. And then for B times A, if we look at the inner numbers, they're both 1, so that means that we can do the multiplication. And then we look at the outer numbers, and both of those are 3, so that means that the size is going to be a 3 by 3.
Okay, I see. Thank you.
Okay, so that's how you can know if you can do the matrix multiplication first, and then what the size is going to be after. Alright, so everyone clear on this? We'll do a few examples so we can kind of get a better idea too. Did I spell that wrong? Okay, let's do some exercises here. I don't want to do that yet. Okay, I'm going to make these up on the fly. So let's say we have a vector A here of 1, 2, 3, 4, and a vector B of 5, 6, 7. Okay, so let's do R equals A times B, and S equals B times A. Alright, so I want you to think about this on your own for a minute or two.
Supposed to be a column or a row? Are they supposed to be columns?
Yeah, it's supposed to be a column, yeah. Okay, so I want you to think about this on your own first for about a minute, and think about if we can do both of these matrix multiplications right here.
I think you could only do B times A. Only S.
Okay, yeah, we'll talk about it. Okay, so hopefully all of you are able to think about it. So let's first write out the sizes that we have for both of these. So for A, we have 1 row and we have 4 columns. So we have 1 by 4. And then for B, that's a column vector, that's 3 by 1. So if I'm doing A times B for R here, we have, let's make a comment, we have 1 by 4. And then we're doing this multiplied by 3 by 1. Alright, so our inner numbers, they don't match up, they're different. So I'm not going to be able to run that line. So if I run our script here, and it tells us that we have an error. It says that we have incorrect dimensions for matrix multiplication. And it even tells us, check that the number of columns in the first matrix matches the number of rows in the second matrix. And then it tells us, okay, yeah, maybe you didn't want to do matrix multiplication. Maybe you meant to do element by element multiplication, but you forgot to put a period. So if we did that, then we could do element by element multiplication, but for our example here, that's not what we want. Okay, so we can't do R because those inner numbers don't match. Alright, let's take a look at S now. So for this, let's make another comment. We have B, that's a size of 3 by 1. And then we have A, that's a size of 1 by 4. So our inner numbers, they're both 1, so that means that we can do it. So Nathan, you were correct. We can do it. And then we look at the outer numbers, and that's 3 and 4. So that means that we're going to have an output of 3 by 4. So 3 rows and 4 columns. Let me suppress this. Alright, there we go. And you see that we have 3 rows and 4 columns. Alright, everyone clear on that? We'll do a few more here too. Alright, let's say we have C equals 10, 20, 30, 40. So that's our row vector. And then we'll do D equals 20 and 10. Need a semicolon. Okay, and then let's do... I guess I should have made this a capital S. Something equals C times D, and other equals D times C. Okay, so think about this on your own, and think about if we can do either of these matrix multiplications.
It's the same thing as the other one, though, right? Because the columns and rows are equal, so you can only do D times C.
Yeah, well, think about it on your own, and then we're going to talk about it. Okay, so let's go over this now. Let's write out the sizes again. So here we have 1 row, and we have 4 columns. 1 by 4. And then here we have 2 rows and 1 column. So we have 2 by 1. Okay, so for something, we're trying to do 1 by 4, and then multiplied by a size of 2 by 1. So those inner numbers, they're different, so we can't do it. So we're going to get an error. So if I run this, it tells us on line 99 that we got an error, so we can't do that. Then if we look at line 100, we are multiplying a size of D times C, so we have 2 by 1, and then C is 1 by 4. Alright, so our inner numbers, they match, they're both 1, and then the outer numbers are 2 and 4, so that means that our output is going to be a 2 by 4 matrix. Alright, so we have 2 rows and 4 columns. So yeah, it was similar to what we just did, but the output size was different in the end. Okay, and then we're going to move on to matrices as well pretty soon here. But is everyone clear on this before we move on? Okay. Let's move on. First, both row vectors this time. Didn't we do one of these before? No, maybe not. This will kind of also explain matrix multiplication and element-wise multiplication. Okay, hold on.
Oh, we covered a lot today, so.
Yeah. Because Zoom tries to save automatically the recording, but I'll check after class. Because I didn't get a pop-up, so that's kind of worrying me. But I'll see. Okay, so when did I start lagging before I talked about vector multiplication?
I think so.
Yeah.
Okay.
Just start over from the slide.
Yeah. I'm gonna start, right here. Cause I'm gonna go over this one more time. I think you guys got that, but I'm gonna go over that again. So when we looked at this example for something and other, okay, it was after number 2? Okay, well, I'm still gonna talk about this. So the inner numbers were different for something. So we couldn't do that multiplication. Then on line 100, the inner numbers were both 1, so we can do it. And then we look at the outer numbers, which are 2 and 4. So that means our size is going to be 2 rows and 4 columns. Alright, so vector multiplication. So if we try to do matrix multiplication between two vectors that are like 2 row vectors, we're not going to be able to do it. Because this time, we're going to have, let's look at this example here. The number of columns in Z isn't going to be the same as the number of rows in Y, right? We have a 1 by 3 and then a 1 by 3 again. So, this might be a little redundant to what we just looked at, because we looked at, now to look at the sizes here, these inner numbers. But this is just kind of also a baseline rule that we can't do matrix multiplication between two vectors that are of the same dimension. Okay, so we know we can't do this multiplication, again, because we have 1 by 3 and 1 by 3. But we can do, of course, element by element multiplication here, where it would basically make a whole new row vector, that's a 1 by 3, and it would do 3 times 6, 0 times 6, and 3 times 6. Okay, so now let's do it with a matrix. So we have vectors so far, but now let's throw in a matrix here. I'm going to do vector matrix multiplication. So let's get a vector P. We'll say that's 34 and 29. I'm also going to put the size here. So we have 1 row and 2 columns. Then we have a matrix J. 2, 10, and 4, 9. Okay, so we have a 2 by 2 matrix. So if I want to look at P times J, so we have P times J, doing matrix multiplication, of course, remember that. And here, let's make another comment, we have 1 by 2.
It's gonna work, the inner numbers are the same.
Mm-hmm.
You can't do it with the other one, though.
So we have a 1 by 2, and then we have a 2 by 2. So right, we look at the inner numbers, and they're both 2, so that's good. Then we look at the outer numbers, that's 1 and 2. So that's telling us that we're going to have an output size of 1 by 2. And we do.
Alright, since order matters, what if you want to multiply 3 matrices?
3 matrices, you'd basically have to do the multiplication from left to right with the first 2 first. That would create 1 matrix.
And then
you would multiply. Correct. Okay, so now let's do Z equals J times P, just to be thorough here. So we have 2 by 2, and then we have 1 by 2. So right, the inner numbers, they're different, so we're not going to be able to do line 107. Alright, and in case I didn't mention this before, MATLAB is pretty good also at telling you which line you have an error on. So line 107 in this case. Alright, so matrix multiplication, it's going to be the same thing. So the product for 2 matrices, A times B, the number of columns in the first matrix, in this case A, they have to match the number of rows, and the other matrix, matrix B. So even though we're going on to two matrices this time, the same rules apply. Alright, do A, I'll do 2, 0, 2, 0. B equals 10, 12, 8, 5. Alright, so these are both 2 by 2. So it's same thing again, right? We're looking at the inner numbers. That's 2 by 2, so they match. And then the outer numbers are also 2 by 2. So our output is going to be 2 by 2. So I'll do A times B. We have a 2 by 2. Now, what if I do B times A here? That's still going to work, but our output is different now. So for this is really starting to get into the theory for matrix multiplication, so I'm not going to go over that part, but if you work through it, kind of like, I'm trying to go up here. If you work through it, like some of the work that I showed before, like on these slides, you can kind of go through and see why the output is going to be different. And that kind of relates to me saying before that the order matters. So it matters more than just for the, if you can do the multiplication or not. You know, in this case, it also matters for the output that we get. Alright, so properties for matrix multiplication, you can kind of look through this if you want. We have the associative property, distributive property, and then non-commutative property. So there are some exceptions here, which is going to be the null matrix and the identity matrix. What I would mostly specify on is really talking about these. So I know someone earlier in the semester asked if there was a function to make an identity matrix, so that's the I function. And for zeros, you can make a matrix all full of zeros, or you can make a matrix all full of ones. So you might use ones sometimes for some kind of math operation. But for zeros, that command, we're actually going to use that later on in the semester. So this command again is to make a matrix full of zeros, and we often use it in a script to do something called initializing an array. So we do that usually when we are going to use a for loop, which we're going to go over towards the end of class. But basically, real quick, we would do this, so we would initialize an array to basically save on memory. And again, we're going to talk about what that really means once we go over for loops. Alright, system of linear equations. Kind of talked about this too, right, earlier in the class, but we'll go over this now. So here we're not doing it element by element, so we're not going to put in a period. But you can imagine that we have this system, or this linear system of equations here. So this is literally going to be, you know, a question that you have in your math class for 250B. So if you solved it by hand, you could go into MATLAB and check your answer. Alright, so you see that we have three equations here, and we have three unknowns, right? We have x, y, and z. So we can go into MATLAB, and we can construct a matrix which will be consisting of all these numbers on the left-hand side of the equal sign. So we have A equals 4, 20, and 5, 2, 4, 3, and then 5, 12, 9. And we have B. B is going to be a column vector. You might hear this called a forcing vector as well in some of your later classes. So that'll be 50, 8, and 40. So that's a column vector that consists of all these values on the right-hand side. And if you want to solve for x, y, and z, we're going to do the left-hand division. So I'm going to call this solve for solution, then A divided by B. And then there we go. Here's our answer for x is -16, y is 3.55, z is 8.6.
What if you try a regular division, left-hand division?
So if I try right-hand division?
Like regular division.
Yeah, so that would be like that, and then it wouldn't work in this case, because the matrix dimensions are different.
Those like multiplication, same rules for that or what?
Well, division with arrays is really kind of weird. That's when you start to talk about getting the inverse of a matrix,
Okay.
and that gets more into the theory for like your math class that you'll take.
We'll done with later then, I guess.
Yeah. All right. Matrix exponentiation. So for this, again, I don't want to get too in depth for like math theory, but matrix exponentiation. So if you had a matrix A and you wanted to square it, that would be the same as doing A times A. And to do this, we need to have a square matrix. So that means that the number of rows is the same as the number of columns. So in MATLAB, we can do this just by A squared, but in your math class, you're going to actually have to carry out that entire matrix multiplication yourself. So you'd actually be doing it like A times A. Alright, you can use the cross product as a function in MATLAB as well. I'm not going to talk about this too much. And then you can also do the dot product. So we're not going to use those in this class though, so I don't want to go over them in detail. Alright, and then polynomials, we have a bit more to go over for polynomials, so we'll talk about this next time. And that's going to kind of lead into plotting, and that's going to be our next chapter. So we're going to do that. We're going to get started on that next class. So as for homework, I'm going to assign homework today. I still have to make it though, so it's going to be posted later today. And that'll be due on next Monday. And your quiz will be sometime next week. I'm thinking Monday right now, but I'll let you guys know on this Wednesday. And I'll try to get your quiz 2 grades in by this Wednesday as well. Alright, so that's all I got for today. So if you have any questions, feel free to stick around.
Thank you. So no homework assigned today, or?
I'm going to assign it today, but it's going to be posted sometime later today whenever I finish making it. Yeah.
Thank you. Goodbye.
Yep, see ya.